Okay, so all the values can be inserted in. We talked about how um, we start off with the right triangle, which is Pythagorean theorem, relating all the sides. We find the derivative. Every variable gets time treatment, meaning that there's always going to be a d over dt for that variable. So every time, so we do power rule like before, we just have to attach an appropriate derivative differential variable for each of the variables that we are working with. So that's how we end up with 6 variables. We read the problem to figure out where the values go. And anything that has a movement or a rate to it, we have to put that in for a d over dt. Anything that is a static value, then that's your x, that's your z. We're unable to find y initially because that wasn't given to us explicitly, but we could go through Pythagorean theorem and find that y value. dz dt, the reason why the rate of change of the ladder is 0 is because the ladder never changes its length, right? It's 25 feet at the beginning of the problem. It's 25 feet at the end of the problem. So it has not changed at all over the course of the entire problem. That's why dz dt is 0.
So it's always going to equal like you're always going to try to have the dy dt by itself.
Well, for this problem, yes, but
right
for whatever variable. Sometimes we may have a similar triangle. A triangle problem where there's a different motion to the problem. If that's the case, we have to kind of think about what that motion is looking like. But yes, but you're right. It's ultimately always going to be one variable that you're trying to solve for, and then all the other variables we should be able to find a replacement for.
Okay. I have a question. So like, I feel like with these problems, I struggle with like trying to like find the variables. So like how do you know like which variables you're looking for? Like looking at the problem.
Right. So for this one, it says how fast is the top of the ladder moving, and in which direction? So the top of the ladder, if you think about the motion of the top of the ladder, it's either going to go up or go down, right? There's only two ways that the top of the ladder can move, and because it's getting pulled away from the wall, it has to be moving down. And if it's moving down, it's referring to the y variable. But if there's movement involved, it can't just be y, it has to be dy dt. So I think it's a matter of looking at the problem, visualizing it, and then kind of narrowing down your choices.
So are they all going to involve like movement of some sort?
Yeah, all the problems will have some sort of a change, a rate of change.
And that'll be a derivative.
And that's usually derivative, right? But the hope is that you're not going to get to the quiz and it's like, well, I've never seen this scenario before. It's going to be scenarios that you've seen before. So it's not going to, so if we do enough of these, you're just practicing and getting yourself ready. You're not going to get a whole brand new situation you never experienced before. So hopefully after enough practice, you'll feel comfortable with all the different scenarios that we're going to see. Okay, there's a part B to this part. Well, first, any questions with being able to get that -9/4? Let me talk about plugging everything in here. This ends up giving me 90. So I get 90 plus 40 dy dt is equal to 0. And that 0 is nice. It wipes out everything on the right side because that dt is 0. And then I can subtract 90 from both sides, divide both sides by 40, and I get dy dt equals -9/4. The units of measure, think about this here. Y is in terms of feet. T is in terms of time. So that's why our units of measure is feet per second. So anytime you're trying to decide, wait, what's my unit of measure? Look at your variable. Your variable should give you enough hints and clues as to what you need to build your units of measure or to identify your units of measure. Okay. Now there's a part B to this. Part B says, at what rate is the area changing when the bottom of the ladder is 15 feet from the wall? So it's the same scenario as what we gathered from part A. But now we're talking about the rate of change of the area of the triangle. But let's build the formula first, right? What is the area
of this, because we see the shape in front of us, right? That's an area, that's a triangle here. What's the area of a triangle formula?
Base times height divided by times 1/2.
Yeah, so 1/2 base times height. Now, in terms of the variables that I've already established, I'm going to use x and y. So my area is 1/2 x times y. Okay, we're trying to find what variable do you think we're trying to look for here? What are they asking for?
Right, dx/dt.
It's close. D what? At what rate is the area changing?
dA.
dA over dt. Okay, we're looking for dA dt, which means we got to find the derivative. But look at the setup on the right side. What's required here if I want to find the derivative? Okay, yeah, we definitely have dx dt and dy dt showing up, but there's something else. Product rule. I can't just say 1/2 dx dt times dy dt. These are being multiplied. I got to go through product rule. Now, if for some reason if it was 1/2 x plus y, I could make it 1/2 dx dt plus dy dt. But the fact that there's a multiplication of two variables, and I want to find the derivative, I got to go through product rule. So I'm going to just let that 1/2 x be f, and then I'll let the y be my g. So let's build out our derivative here. A becomes dA dt. Okay, f prime g plus f g prime. Okay, so let's do this one piece at a time here. What does 1/2 x turn into? 1/2. Remember, everything has time involvement now. X has something left over as well. 1/2 x becomes 1/2 dx dt. Okay, the g doesn't ask for any changes. It just asks us to bring down whatever we see under g, which is y. Back to f. F has no changes, not asking for any changes as well.
dy dt.
And then finally, yes, g prime is going to be your dy dt. Any questions with this? Okay, so now we just plug everything in from part A. We have dx dt, we have y, we have x, we have dy dt. So all that just gets put together, plugged in the calculator. Right. But let's explore the units of measure, though. What do you think the units of measure is going to be? I need something area and time over each other. What's the area unit? Feet squared. Good. Area is a two-dimensional unit, feet squared. And time is seconds, right? So square feet per second or feet squared per second.
So there's just like parts of this problem. What I usually ask you for like area or something.
Yeah. If there's a second part, it usually asks you for area, right?
They won't ask you to find one of the variables he's already found.
Right, yeah. There's no new variables to find except for dA dt, right? Everything else we can pull from part A.
Okay, next page, whenever you guys are ready.
Okay, anybody still need this page? Okay, next up, a spherical balloon is being inflated at a rate of 10 cubic centimeters per second. Find the rate of change to the surface area of the balloon at the moment when the surface area is 64 pi. Okay, we're dealing with the volume and surface area of a sphere, and these formulas will be provided for you. Same thing on the AP exam, they'll give these formulas to you if a problem involves these formulas.
What's that a volume for?
This is volume for a sphere. Volume and surface area of a sphere. Okay, before I gather any information, I know already that I have to involve the derivative somehow. Let me just want to go ahead and get my derivative out of the way, just so I can have all the variables in front of me, and then all the resources in front of me for me to solve the problem. Okay, let's go ahead and just get the derivative out of the way. Now think of now there's no need for product rule, okay? Pi is just a number. There's no like f and g here. This is just some coefficient that's hanging out in front of the variable r. I'll put this over on this side. Okay, let's go through a derivative here. What does v become? dv over dt. 4/3 pi, that's not going to go anywhere, just a number that happens to be in front of my variable. Power rule is going to impact r cubed though. What's the derivative of r cubed? Okay, 3r squared. Anything else? dr dt. Okay. Okay. Any questions here? Okay. Now, in terms of cleanup, what can I do to make this a little bit less messy? 3's cancel out. Okay. All right, so I'm going to have a cleaned up dv dt here, which I can use in a second. Okay, we'll come back to that when we need it. Let's build out the derivative for s. All right, what's the derivative for s here? S becomes what? ds dt. 4 pi isn't going anywhere. R squared becomes dr. Yep, 2r dr dt. Okay. 4 and 2 multiplies together. I made that 8 pi r dr dt. So I want us to just recognize, we may not need all these equations, but we do have 4 equations available to use if we need to kind of piece things together. Okay. So now let's gather some information here. Let's reread the problem. The spherical balloon is being inflated at a rate of 10 cubic centimeters per second. Any idea what this is? What is this referring to? Here's the hint: cubic centimeters per second. Cubic centimeters is a unit for what? Volume, right? But per second. So I need volume, I need time. What's the only variable that's going to hold that information? dv over dt. Good. So sometimes it doesn't say, oh, that's the volume, but the units is what you're going to use to kind of help you narrow down your choice. Now, every time I put down a rate, I got to decide, is it a positive or a negative rate? And what do I say here based off of context clues? Positive because Yeah, it's inflated. It's getting larger, right? This balloon is growing in its volume. So 10 cubic centimeters per second. Okay. Find the rate of change of the surface area of the balloon. Find the rate of change of the surface area of the balloon. What are we looking for? ds over dt, right? Rate of change of surface area is not just s. It has to be some sort of a movement involved there. So ds dt is our goal. At the moment when the surface area is 64 pi. That's just what? That's just s. Okay, we're looking for ds dt. We have a formula for ds dt. Ideally, we can just put information in and then just find ds dt, right? So we need r and we need dr dt. Okay, that's what we need. If we have those two things, then we can find ds dt. But do we have the radius or the dr dt right now? Not explicitly, but they do give us something that may be related. So we may have to kind of do this little puzzle thing where we use one information to find some other information. And then over the course of these equations, maybe we can eventually get to what we're looking for. So we don't have r, we don't have dr dt, but we do have s, we do have dv dt. So let me start here. If the surface area is 64 pi, is there some useful information that we can get out of this information, out of this piece? Okay. How can this help us out? Yep. Good. So if I can plug 64 pi in for s, that will give me the ability to solve for r. If I solve for r, then r is one of the pieces that I need for ultimately my ds dt. Okay, let's try that first. Okay, I'll divide both sides by 4 pi. I'm just trying to solve for r here. 64 divided by 4 is 16. Take the square roots. Okay, so I have a piece of the puzzle there, r equals 4. So I know I can get there, okay? So that's one piece that I need. I also need dr dt, but I don't have dr dt yet, but they do give us dv dt. So how can dv dt help us get to where we want to be? Good. And then if I have 10 in here, I now know what r is, right? R is 4, and that gives me the ability to solve for dr dt. And if I can solve for dr dt, then I have the two pieces that I need to get to my answer. All right, so I'll put the 10 in for dv dt here. I'll put the r squared being the 4. Now, when you use your calculator, don't put pi in the calculator, okay? I want your answer to be exact. So treat pi, I know pi is not a variable, but in this sense, I do want you to treat it like a variable in the sense that I don't want you to put in the calculator. I want you to hold on to that symbol throughout the entire problem. Okay. So if you plug the calculator, you lose the ability to get an exact value. It'll start to give you approximations. Okay. So 4 times 4 squared is 64. So 10 equals 64 pi drt. I'm running out of room here. I'm going to put that over here. Okay, does everybody see the progress that I made here? Okay, I'm almost there to my end here. How can I solve for DRDT? It again? Good. 5 by 64 pi. Now, there's something that I wanted to point out. Where is pi located in your fraction? Denominator. So it needs to stay in the denominator. I think the tendency for us is we tend to feel more comfortable if the pi is in the numerator, and we think that we can just let that pi be in the numerator. It's in the denominator. It needs to stay there. Even when we clean this up, we can't just let that pi float up to the top. I mean, sometimes the answer is the pi in the numerator, but sometimes if it's in the denominator, we need to let it stay in the denominator. Okay, so I just want to point out that's something that I see students do. They feel like that pi is out of place and they just move that pi to the numerator. But trust your algebraic steps, right? If your pi is in the denominator, just let it stay there. Okay, 10 to 64 can reduce. I can take 2 out of both of these, so I get 5 over 32 pi. And I understand the reason why students want to bring that pi up to the top. It feels like something is wrong. It feels like that's in the wrong place, and that's why they put that pi up top. Yes, question.
How you got the 64 pi?
Oh yeah, so I cleaned this up here. I did 4 times 16, and I made that 64, and I just moved it in front of the pi, and I made it 64 pi. So I went from here to here. Yeah, sorry, I ran out of space here, so I moved my work over to this right side here. Okay, do I have enough information now to solve for DSDT? Yes, yep. I have my R, which is 4. I have my DRDT, which is 5 over 32 pi. And now I can solve for DSDT. So DSDT equals 8 pi times 4 times DRDT, which we found to be 5 over 32 pi. Okay, this cleans up nicely, actually. What's 8 times 4? 32. There's a 32 in the numerator. There's a 32 in the denominator. I can take that out. And I can also cross out what? Yeah, I got a pi in the numerator, pi in the denominator. So the only thing left is 5. What's my unit of measure? Just think about the variables in play here. Surface area, surface area. Keyword is area there. So what's the unit for area? Centimeters squared. Yep, and time is seconds, so centimeters squared per second. All right, yeah, go ahead.
I'm kind of lost a little bit.
Mhm.
Are we gonna have a lot of practice with this?
Yeah, we will.
Okay.
But yeah, I know there's a lot, but yeah, ask questions of any parts that you want me to repeat.
Like, how do you approach a problem like this? How do you
Yeah, so so the formulas are given, and with related rates, you're always going to be involving derivative. So we just want to go ahead and find the derivative, and we know that, okay, we have everything in front of us. This is the only calculus here. From here on out, once we get this out of the way, the rest of it is just algebra. There's no more calculus. You're just putting information in and solving for whatever variable you're looking for.
What does the dV over dt have to do in relation to ds?
Right, so dV/dt is the rate of change of the volume of the balloon, and ds/dt is the rate of change of the surface area of the balloon. And they give us information about the dV/dt, but they're asking for the ds/dt because it says find the rate of change of the surface area of the balloon.
So we use the dV/dt to help us get to.
Yes, we use dV/dt to help us get to one of the variables that we need to get to the ds/dt. Yes.
When is it?
Next week, either Tuesday or Wednesday. I got build that, I gotta look at the calendar and get that. I'll give you a new calendar by Thursday, Friday for the next month. Okay, we'll do more practice with this, but any questions? Ultimately, if you look at, this is really the key equation here, right? You're looking for DSDT. We need R, we need DRDT, but if they don't give that to us initially, we have to kind of use what's given to us and work our way to the variables that we need to get to DSDT. Okay, we're gonna skip number 4 here. 4 is Pythagorean theorem problem, but it's just a strange setup. Not going to worry too much about that. The next piece is the cone problem. The cone problem, I would say algebraically is the messiest one. So we'll definitely spend time with this. First time through, we're just going to try and kind of follow along. And then by the time, hopefully the second and third time, we'll just get more comfortable with the way that's required to set this up. Okay, so we have a conical tank, vertex down, 10 feet across and 12 feet deep. If water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change to the depth of water when the water is 8 feet deep. So first thing is the volume formula will be given to you. This is the volume of a cone, pi over 3 r squared h. Okay, so that will be given to you. There's no need to memorize that. Now we're going to be finding some variable that is going to be built once the derivative shows up. But one thing I want you to notice is that there are a lot more variables here than previous problems. There's too many variables. If we find the derivative using product rule, we're going to be left with too much information or too many variables, not enough information. So we have to find a way to get our radius and height down to one variable. And the good thing here is that we can actually find a relationship between radius and height because of the way that the cone is shaped and because we have similar triangles that we can use to create that relationship. Okay, so there's going to be some water level inside, and there's also going to be a cone that is a smaller cone shaped by with the shape that the water takes on. Okay, so if you can imagine, there's a cone that is set in stone, and then there's a cone that's ever changing because water is flowing into the tank. Okay, so I want us to look at this cross section here. Okay. So I want us to make an observation here. We want to break this down into radius and height. So it says it's 10 feet across. That's the diameter of the container. What's the radius of this container? Container? 5. Right. What's the height of the container? 12. Okay. Now that's set in stone, but is the radius and the height of the water level always changing? Yes. So R and H. Okay. So I'm going to step to the side here, and I'm just going to focus on what I shaded in. And you see that we basically have a triangle within a triangle. Because of that, we can create portions and relationships involving this information. So radius 5, height 12. Okay. Okay. Do we understand why there are numbers there and why we have some that are variables? Okay. The unchanging portion, we can put numbers in. The changing portion, we have to put variables in for them. So here's how we can build a relationship. We can say the radius of the small cone is to the radius of the large cone as the height of the small cone is to the height of the large cone. Everybody okay with this relationship here?
So there's a smaller cone and a larger.
Yes, there's a smaller cone and larger cone. The water inside the tank is going to take on the shape of a cone. Does that make sense? So, yeah, the water that's inside is going to you treat that like it's a smaller cone inside a larger cone.
That makes sense.
Okay, I'm going to cross multiply here. I'm going to say 12R is equal to 5H. I'm going to pause this portion of the problem for a second. And I want to go back and gather some information because we don't know which variable to solve for until we get more information. Okay, so we'll take a pause here and we'll go back and just identify some information. The conical tank is 10 feet across, 12 feet deep. We already gathered that information. If water is flowing into the tank at a rate of 10 cubic feet per minute, water is flowing into the tank at a rate of 10 cubic feet per minute, what variable is going to hold that information? Yeah, you know cubic feet must be volume, but then minute, this time component, so that's dV dt. Okay, so let's put that here, dV dt. Positive or negative 10? Positive, because water is growing inside, there's more water building the tank, right? The tank is gathering more water. Find the rate of the depth of the water. Find the rate of change in the depth of the water. Any idea what variable that could be referring to? We don't see it yet, but
That's
d something.
dV.
Well, dr is going to be the radius. The depth is more referring to the what? The height, yeah. So dh dt is the unknown. When the water is 8 feet deep, h. Okay, I want you to put a star next to this variable, this value here, because it's easy to misuse this. We don't want to touch this until the end. Okay, so do not use until the end.
You still have the feet label to it.
Yeah, I should put 8 feet here. Okay, so we're going to ignore this information until the very end. Okay. And the reason that I want us to say we ignore it because the temptation is you want to put that 8 wherever you see the h, but it's not ready yet. Okay. H is still changing. After we find the derivative, once we have things set in stone with the derivative, then we can involve the 8 feet. But if we set 8 too early, then we're saying that the water level is staying at a height of 8 feet for the entirety of the problem, which we know is not true. So we want to hold on to variables when things are changing, at least until after we've created some resolution. So what are we looking for?
For the change.
dH dt, right? So which variable would we prefer to keep if we want dH dt to show up? H. Okay, does that make sense? We would like H to remain because H will naturally produce a dH dt for us, which means that we want to get rid of what?
R.
R. Okay, so I want to replace R. Okay, do I see a relationship between R and H? This one here, right? So what variable can I solve for if I want R to disappear? R. Yeah, I'm going to solve for R. That way I can replace R and I can create an equation in terms of H. And then when I find the derivative, dH dt will show up and then we can start putting information in. Okay, so I'm going to go slow here. B equals pi over 3 R squared H. We want to find a substitution for R. We're going to solve for R here. If I solve for R, what's R equal to? Good. 5H over 12. Okay, so I'm going to put that into the volume equation. Okay, so I'm in a substitution phase here. Pi over 3. What's my R again? 5h over 12, but it's not just by itself. I got to do what with it? Squared times h. Okay. Is the radius removed from my equation? Yes. Okay, so that's a start. Now, we want to do some cleanup here. We don't want to do the derivative just yet because this is too messy. Otherwise, you got to go through product and chain. There's no need to do that when we can just clean everything up and just do power rule. Okay, I'm going to distribute the 2 through each of the terms inside, and I'm going to clean this up. So V equals, what is this? How's the square going to impact what's in here? Good. 5 is squared, h is squared, 12 is squared, 25 h squared over what? 144 times h. Now, if it helps, that h is in the numerator. If you want to put a 1 in the denominator just as a way of knowing where the pieces go, that's fine. All right, I would like to get all the coefficients together and all the variables together. H squared times h is going to give me what?
H.
H cubed. Okay, and I'm going to put this all out as a fractional coefficient. So 144 times 3 is 432. The 25 and pi can go together, and I'm just going to push it out as a fraction. I want that h to be by itself. I don't want to see anything below the h, which just makes it messier. So I have 25 pi over 432 h cubed. Okay. To get to this point is the hardest part. All right. So look back at what we've done up to this point. Any questions as to how or why we're able to get to this point?
So you distributed the squares, so like you made the power.
Right, I'm not ready for the power rule. If I want to do the derivative, I got to go through product and chain, and that's too messy. I would prefer to clean it up and just rely on the power rule once I get it all cleaned up. Good. Any other questions up to this point? Okay, so now we're ready for the derivative, right? Everything is nice and clean. There's just some, I mean, it's a messy number in front, but that's just a coefficient, right? Okay, so let's build a derivative. V becomes dv over dt. What's going to happen to this? Okay, yeah, you're right. I do want to slow down a bit, but this stays, right? We're not going to do anything with this. It's the h cubed that's going to get impacted. H cubed becomes 3h squared dh dt. Okay. Coefficient stays. H squared becomes 3h. Sorry, h cubed becomes 3h squared dh dt.
Coefficient stays, but normally it just disappears.
Yeah, good question. So if I ask you if y is equal to 4x squared, what's the derivative of 4x squared? 8x. Did the 4 stay? It did, right? So it just so happens that it doesn't quite clean up to be a nice number, but it still stays. Now, if the coefficient was by itself, then it would go to a 0. But if it's attached to a variable, then it's going to stay. Okay, so now we're pretty much near the end. Everything is ready for us to plug in. Do we have h? Which is 8.
12 over 5. Oh,
Well, what do we have a numeric value for h to plug in?
yes, the 8.
8.
Variable.
Do we have a dvdt to plug in?
Yes.
Do we have a variable that we're looking for?
Yes.
Yeah, dh dt. So everything is ready for us to plug in, right? So I'm going to start putting information in here. So dv dt is 10. Okay, you're free to use your calculator, but you do need to kind of dance around that pi there and not put that in the calculator. So you're going to kind of hold on to that pi notation because I want an exact value. As soon as you put pi in the calculator, you're gonna get some decimal value, and it's not going to be exact. Okay, but I'm going to continue to clean this up here before I move that over. So the 25, the 8, 3, and the 8 squared, I'm going to just multiply all that out together. So all the numerators can go together, right? The 25, the 3, the 8 squared, and that gave me 4,800. The pi is going to stay. Okay, almost there. I want to solve for DHDT. I mean, normally I would just say divide the fraction over to the right, to the other side. But dividing by a fraction feels messy, right? So dividing by a fraction is the same thing as what? Reciprocal, right? So I can say 10 times 432 divided by 4,800 pi.
Your final.
Well, let's see if the calculator can reduce it for us, right? So there's that, if you're using a 36 Pro, there's the fractional button that you can use. Now, if you're using the TI-84, most of the calculators are new enough where you have this feature. If you do alpha y equals, there's that n over d feature, which you can get that nice math print to show up. And then you just type in 4320 over 4,800.
Without the pi though.
That's right, without the pi.
And it simplifies it for you.
It does, yeah, simplifies it for you there. That's hard to see.
9 times.
Now, where's the pi go?
Back to the right.
In the denominator. Yeah, we can't push it out and say 9 over 10 times pi. It's 9 over 10 pi. That pi needs to be clearly in the denominator because it's not going to go anywhere, right? Now, what's the unit of measure?
This is height, so it's a speed.
Okay, height is feet, but then there's time components as well.
Oh, feet per second.
Feet per second.
Per minute.
Per minute, yeah, sorry. Yeah, question.
When I put it in the calculator, I got a decimal.
Did you put pi in the calculator?
Yeah.
Yeah, leave the pi
I
out.
usually like don't put it.
Right, don't put the pi in the calculator. Treat pi like a variable in the sense that otherwise we lose that exact value ability. Okay, you guys have homework. Homework is going to be attached here. So you see page 10 and 11. I have all the problems spelled out so you can just work, and I'll send you guys a link to the key so you guys can work that through as well. Okay. Okay, we see that. I put all the problems directly into your packet. Okay, come get your phones.
So